Okay, so we started actually without me doing this. I screwed up, but we haven't hit very much, so I'll just cover it again real quick. Um, oops, I think it was back a slide. So basically, for the video, radiation was found in about 1896. They found that particular elements. I believe it was where is it? Come on, I was just looking at this. Uranium salt crystals would stain a photographer plate even if the plate was covered. And basically, what they're getting out of this is the spontaneous emission of particles coming from the nucleus. Okay, so this is not coming from electrons in outside; it's coming from the nucleus that result from unstable elements. And then we hit this again, this slide right back here. Forget what I said, or remember what I said earlier. Those black dots in the middle of that are, and remember, if you want to see this closer, like there's a lot of small lettering up there. We have these slides online; they're already up for you, so you can be looking at this like while I'm looking at it. Get as close to you as possible here. But yeah, black dots are stable, and everything in the gray shaded area is also an isotope available, but it is going to be unstable. And unstable essentially means it's going to result in some type of radiation. All right. So here, you know what? Let's do this so I don't have to walk behind all the time here. Let's try something a little bit different. All right, so what we're looking at right here is a source in the center putting out three different types of radiation. Typically, that's going to be probably a combination of elements within there that are producing all three of them, because it's not usual that you get an interaction where you're going to get all three of them. We'll talk about how you get all three of them a little bit later. But I think this is where we just ended off before I realized I should have been recording. What are those green X's right there? Magnetic field. And why is it nice to use magnetic field to find these? What is magnetic field going to do to a charged particle moving perpendicular through it? Going to apply it. This right-hand rule, this piece. Okay, so arrow, right? What's your pointer finger? Velocity. Velocity. Okay, so we go velocity like this. I got my middle finger pointed into the board, so it's magnetic field. And what's this? Force. Force on a what? Charge. On a positive charge. Oh, positive. Right? On a positive charge. So what you're noticing, a couple things there, is you'll notice that alpha radiation bends up. What does that tell us about? It has a positive charge. Positive charge. Okay. Gamma radiation heads straight, which means no charge whatsoever. And finally, beta radiation is curving down. Of course, that means negative charge. And you will also note that beta has a larger curve than alpha. What does that mean? It's got just magnitudes. No. I guess that is something it could be. You are not wrong there. It could be more. No. It's faster. Probably means it is less massive. Okay. All right. Now, a lot of those things are things that it could mean as well, but yeah, there's probably more massive in this particular case. All right. So let's talk about. I'm supposed to talk about alpha or beta and gamma. Yeah. Here, let's make sure I'm covering these where I'm supposed to. I don't know if you're gonna hit it again later. All right. So no, I'm supposed to talk about it here. The three types of radiation that can be emitted are known as alpha, beta, and gamma. For emitted particles, a beta particle is so an alpha particle is essentially a charged helium particle. Okay, that is a positively charged, which we discussed an alpha particle the other day. It's basically a helium that has had its electrons knocked off, making it 2e. Okay, gamma is actually just photons. It is just photons leaving an object, so they should leave at the speed of light, which is why they have no charge and why they go straight. Beta is an electron. Now, another interesting thing that comes out of here that we have to discuss are what are known as antiparticles. Now, you're not going to see them up right now. There is beta minus decay, that is the electron, And then there's also beta positive decay, and that is what is known as a positron, which is the antiparticle of the electron. Okay, it is same in all aspects of an electron. It's the same mass, same everything, except the only thing is that its charge is positive, as its name would suggest. So we can distinguish between those in the figure, the radiation from the example. Yep. So each type of radiation have very, very different penetrating powers. In other words, alpha particles can barely penetrate a sheet of paper due to their mass. Let's see, what is it? Beta particles can penetrate a few millimeters of aluminum, and gamma can penetrate several centimeters of lead. So get an idea, of course, there of all of their abilities. Okay. So what we're essentially going to discuss here right now is half-life. Okay, but I'm actually going to get into the math instead of just handing you the equation. We're going to talk about why the equation actually makes sense in this particular capacity. Okay, so here's what we got. There is a random chance that we don't fully know and fully comprehend in many capacities that an unstable nucleus will emit a certain amount of radiation. Okay, when it happens, the likelihood that it happens is dependent on how many particles are there, which kind of makes sense, right? Like if I said there's a 50% chance, or sorry, there's a 20% chance in the next 10 minutes that I'm going to steal $10 from one of you, just okay, then the higher likelihood of me doing that would result from there being more people in the room. Does that make sense? Sorry, now the chance doesn't go up, but the amount of times it should happen go up. Okay. Also, in this particular case, we can see that. So what that first equation says is the change in number of particles over time is directly proportional to how many particles there are. So the more particles there are, essentially, the faster it should decay. Does that make sense? Okay. So how many particles decay? Just rearranging this, if I take this equation over here on the left, and I just do a little bit of algebra, I'm going to multiply T over onto the other side. So the change in particles is going to equal the total number of particles times the time, as we always do in physics. If we're not entirely sure what's going on, guess what this is? Some constant. Okay, so we have this proportionality. We understand this relationship, that the more particles there are, the faster they should decay. Okay, so the change in the particles is going to happen with more particles, and obviously it's going to happen over time, and this little guy would be some materials go faster than others. Make sense? All right, let's continue with the math here. So the rate, essentially, if I rearrange this back, okay, just kind of going right back to here where rate is this guy that I've already underlined, okay? If I take this and I divide delta T underneath, the rate is the change in something over time. So I've got the change in something that's just equal to gamma times N, right? The constant times how many particles are in that particular thing.
Looking a lot like calculus right now.
Yes, as well it should. Okay? So, how many particles are left? I could really get into the math here, but we're not going to worry about it too much on why it's E and why there's all this. Okay, but the number of particles left are equal to this, the original. Come on, I'm trying to write on you then. Okay? No, you're not going to let me? The original number of particles times E to the negative gamma T. Now, essentially, what we can do to kind of shortcut this is we can look at this in terms of half-life. what does a half-life mean? Well, this is literally taking how much is left, how much was originally there, times 1/2, right? Half of the original. Now, because the rate is dependent on how much is there, if I have half, the rate should be half as good. So it should take longer, right? So n is the number of half-lives, or essentially, if you want 2 half-lives, essentially this lays out to is the number of particles you have is the original times 1/2 times 1/2, right? So every half-life, you get that right there. Okay, little n is going to represent this guy right here, okay? Little n represents t, the actual amount of time that has progressed, divided by the half-life time. So we can't just decide how many half-lives have occurred. We need to create an equation to figure that out, because this is dependent on the element in question. So in other words, if I have a sample in front of you, okay, and this sample, so imagine there's a pile of something on the desk, okay, and I said it has a half-life of 5 minutes. What should we see in 5 minutes? Half. What should we see in 10 minutes? A quarter of the original, but half of the half. Okay, so then the question becomes, what do we see at 8 minutes? Right? That's where it gets a little bit interesting. Obviously, it's somewhere between a half and a quarter, right? More than a quarter, less than a half. So what this does is, in that example, 5 minutes would be this. It would be constant depending on what material it is, this underlined part right here. T is how much time has actually happened. When I said it has been 5 minutes, you go 5 over 5, n is 1, that's 1/2, right? You're doing this math essentially in your head. When I said it was 10 minutes, you said, oh, 10 over 5, that is 2 halves, that's 1/4. But if I say 8 minutes, that's where it becomes, okay, so that's 8 over 5, n is now 1.6, and now we can use this math that we already know how to do in order to calculate essentially how much n is left at that particular time. Does that make sense? So if we combine the two of these together, these two last equations, okay, this equation on the other page, okay, told us the total amount is equal to the original amount times E times this constant factor up here, which we got from our understanding that the rate of change is dependent on how much is there. Okay, we combine that with what we were just discussing. What we can do is we can see, just punching in, this was the equation on the other side, okay? This is the equation equal n equals NO times e to the gamma times, I think it was n. No, what was it? Sorry, it was t, yeah, little t. Okay, little t. Okay, so what they've done here is they go, okay, let's plug in half of the element, right? For half of the element, by definition, the time should be its half-life, right? And now we can start to do a little bit of math, and we get this. Number one, obviously, first off, the NO's cancel, and we're left with this guy right here. 1/2 equals this mess right over here. You'll remember that a negative in the exponent means that particular thing is inverted, right? So what we can do is we can get rid of the negative and uninvert. So we have 2 equals e times gamma to the 1/2. And now naturally, to get rid of e, what way do we get rid of e? We put a natural log and then factor out in front. So I'm going to take a natural log of 2 and a natural log of this over here, and then this is going to come out front. So we get this, that the time, the half-life time, is equal to the natural log of 2 divided by this constant. It also means that now we can invert this process. If we measure the half-life of a material, we measure the half-life of a material, and actually we don't even need to weight its half-life per se. I'll show that in a second. We measure the half-life of a material, we can now find gamma, and once we have gamma, we can find that material at any given time. And that way, the half-life will be baked into this constant right here, so that we can go back and continually just use that equation right there. Does that make sense?
And could you say in words what T to the sub 1/2 means?
That is the half-life time.
Half-life time.
That is the, so capital T is regularly used as a constant. Specifically, it's been period, the amount of time that something takes place. The main thing that you want to be able to distinguish when you see a capital T here in physics is you go, that's definitely not a variable, that's a constant. That is something that is set in place. In this particular case, it's set by the material in question.
And then lowercase t is just the.
That's usually the variable that could change.
Right.
Exactly. Yep. All right. So these are just units of half-life. Okay. You will notice that a decay is actually not an SI unit. So technically speaking, what units do we have here? If decay is not an actual unit, what are the units on this? Hertz. Correct. Yeah, it's 1 per second. So it's sort of hertz. Any cyclic thing, anything that happens regularly over time is usually going to be in hertz. But yeah, so they're going to say decays per second. So a becquerel, because he was the most common guy right here, is 1 decay per second. Okay. As you can imagine, this is a lot of times with radiation a ridiculously low amount, given the amount of elements in a thing. I'm gonna take your headphones out there. So what we have here is this, I think this is a short for a Curie. I'll check, but it's defined as 3.7 times 10 to the 10th decays per second. So naturally, combine the two together. 1 Curie is 3.7 times 10 to the 10th becquerel, which is kind of a dumb conversion on the page here, given that we just saw it's, that is 1 decay per second. But there you go. I believe that's a Curie. Let me make sure. I don't choose to. Yep, that's right. CI is a Curie, and BQ is a becquerel. Yep. Most common units that you're going to see, though, are millicurie and microcurie. While it does happen quite a bit, it doesn't happen that many times. All right, true or false? A radioactive atom always decays after 2 half-lives have elapsed, meaning all the material is gone after 2 half-lives. Is that true or not? Nope, that is not true at all. What fraction of a radioactive sample has decayed after 2 half-lives have elapsed?
3/4.
What's that?
3/4.
3/4, correct. Yeah, so keep in mind there that says how much has decayed, not how much is left. That's usually what we're referring to. Yeah, so this would be 3/4. Which of the following, suppose the decay constant of radioactive A is twice the decay constant of radioactive B. If the substance B has a half-life of 4 hours, what is the half-life of substance A? So that was the decay constant of radioactive substance A is twice that of radioactive substance B, and it tells us that substance B has a half-life of 4 hours.
Lambda is not the decay constant?
Hmm?
Lambda is not the decay constant?
Correct, yes. Yeah, lambda's a lot of things. As a matter of fact, all the letters are a lot of things.
Including K.
Including K.
K is that.
So what do you got? What should it be? Keeping in mind that here is your equation right here. Oops. Nope. I was miswriting already. Yes, should be 2 hours. So basically, it's inverted, right? It's just an inverse relationship here. So if the half-life, sorry, if the constant is bigger, it means the substance is decaying faster or less amount of time. All right, this is a different conversation. So we did beta decay real quick. Where are we at here? Just to roughly give myself a spacing of time. 29 to. Maybe we should probably put it like I said. Okay, so this is going to be some super basic math right here. Okay. You see a lot of decay, and ultimately predicting what type of decay comes out of an element is, from my understanding, relatively foolhardy. It's mostly a matter of experimentation and observation on which one of these happen. So all I'm looking for you to do right now is basically use your periodic table to kind of see what should be left. Meaning, this gives you formulas up here, but I think this makes it look way more complicated than it actually is. So let's see it in action. Okay, so beta decay on uranium-238. Okay, uranium-238 starts.
So this is beta decay right now?
Sorry, no, alpha. This is alpha. I misspoke. Yeah, this is alpha decay on uranium-238. So basically, here it is in a nutshell. Uranium-238 over 92. Remember, what is the top number?
Number of things
In the nucleus. So why is alpha? Yeah. Why is alpha got a 4 over 2? Because it's a what type of atom?
It's helium.
Helium, and its standard isotope is 4. Meaning, what does a helium's nucleus look like? 2 neutrons, 2 protons. Right. So essentially, what we got here is this. We got 4 things came out of 238. So how much is left over? 234. Right? And 2 things came out of the proton. So number 92 switches to 90, and then you look at your periodic table and see which element is 90. Thorium. There you go. Simple stuff. Okay? Ra versus Rn. I believe Ra is radium. Rn is radon. Yes, I agree. Okay? So, radium, same thing showing you here. You're just seeing super simple math. What I would suggest you do is probably write this, write the arrow, write this over here, and then just kind of do the math in your head and go, hey, there's 4 taken away, 2 taken away. Pretty easy stuff. Yes, we don't need to kind of go further beyond that. These are basically writing balanced equations. Okay. Alpha decay. Before decay, and after decay. Well, before the decay, you'll notice there's no kinetic energy, assuming the object is just kind of sitting there, and there's no momentum because it's all one thing. It's just sitting there. But after the decay, both the radon and the alpha particle will have kinetic energy, okay, and they are now traveling away from each other. So where does that energy come from? We can't just get energy from nothing. Where's it coming from? The binding energy, correct.
Hold on, stay.
Okay. I've shown you this previously. Kinetic energy is momentum squared over 2m, right? That's just a rearrangement of 2mv squared, just to show it again super fast. K equals 1/2 mv squared. So if I put in another m on top, I need to put another m on bottom, and so this becomes p squared, and the bottom becomes 2m. It's just a nice way of, like, instead of going, if you don't do that, you've got to go all the way to velocity, and then you've got to go all the way back, and this just gives you an equation. So if you already have momentum, you'll be all set. So you're going to have to do some calculations there that you already know how to do. So I'm not going to spend a lot of time on it. I do want to make sure I'm not missing anything on that slide, though. We already talked about that. All right, so for alpha emission to occur, this makes sense. The mass of the parent particle, so the radium up there, must be greater than the combined mass of what are called the daughter, that would be the radon right there, the daughter and the alpha particle. Excess mass is converted into energy of other forms. Okay, converted into energy of other forms appears in the form of kinetic energy and of those particular particles. Most of the kinetic energy is carried away by the alpha particle because it's less massive than the daughter nucleus. We understand this because the alpha's kinetic energy and momentum are certainly related, which we see right there. All right. Beta decay. So beta decay is interesting because remember I said a second ago that beta decay is what? Which one's beta decay? or positrons. Now, here is the interesting thing out of this, though. You go, oh, electrons, we've done this already, except no, we haven't. These are not electrons that are being emitted from the electrons. Where are these electrons coming from? Why is that a bit strange? You shouldn't be there. There's no electrons in the nucleus. Well, sort of, and we'll get to that here in just a minute. Okay, but essentially, what it comes down to, actually, I say we're going to get to it in a minute. I think we're going to get to it right now. Okay. Kind of. I want to make sure to say this right. I wish they would have done this before. Oh, it's on the bottom. Okay. So here's an example real quick. Actually, I'm going to skip down to the bottom real quick. So here it is in a nutshell. A neutron, in a large way, is a proton plus an electron. Okay? And a neutron is also a positron plus an antiproton. Okay? Every particle has an antiparticle. The difference between them is simply charge. That's it. Okay? So, in this vein, here's what we have. If we shoot an electron out, what have we lost? Look at this equation right there. If we shoot an electron out, what broke down? What split apart? Looking at the last line. No.
Neutron.
Keep in mind, by the way, okay, what is the reason why these atoms are unstable? They have too many neutrons, right? So it kind of makes sense then that a neutron would then break apart, okay? Now, if the neutron breaks apart and an electron skips out, what's left over? A proton. So has the nucleus gained or lost a total number of things? No. It has just as many protons plus neutrons, it just has one less neutron and one more proton, yes? So notice the top number up here, A, isn't changing. But we have one more proton, which means what about it? It is now a different element. It is plus that particular guy right there. Okay, so this goes up one. So you see with carbon right here, carbon 14, if it goes through, excuse me, if it goes through beta emission, would shoot out an electron by turning a neutron into an electron and a proton. So again, you have 14. So right at the beginning here, 14 means we have 6 protons and 8 neutrons. But one of those 8 neutrons just became a proton. So we still have 14 things in the middle, but we now have 7 protons in this particular case. So now it is no longer carbon, it is now nitrogen. Nitrogen 14. Now weirdly, nitrogen 14 should be, no, that's right. Nitrogen 14 weirdly is more stable. Now, this line right down here is obviously going to be weird to you, and I understand that. And a large part of that, I will tell you, comes from the elementary understanding, the elementary particle system, like the particle model of the universe. So we will talk about that a little bit in the next chapter, but for right now, we just have to trust me. All right. So here's the deal with this process. In beta decay, oh, I'm sorry, I wanted to talk about the other one as well. So what is this line right here? What is the second line? So this one was shooting out an electron. Nope. This is also leaving. We're still positive on that guy. That is a positron, correct. That is shooting out a positron. Now I said earlier that a neutron is either a proton plus an electron or a positron and an antiproton. And what's true of an antiproton? Negatively charged. Okay, so let's talk about this equation real quick. So what we have left over in the nucleus is a antiproton, which is a negative charge, which usually there are all positive charges, right? Now, the other protons that were there are unaffected. You just have gained an antiproton. But if I have, say, just making up a number here,
if I have 8 protons, and now I've added 1 positron, okay, again, I haven't changed the total number of things in the nucleus, so A stays exactly the same. We have lost a neutron, but gained a positron, we're good. That being said, what about the amount of protons there? Well, in a way, the main factor that a positron and the antiparticle will do is if two of a particle and an antiparticle collide, they will eliminate. So what is this antineutron going to do to one of the protons? Going to eliminate them, and so we have one less, which is why you see that -1 right there.
So does that just eliminate it entirely, or
Yes,
like
from
turn it into a
existence.
neutron? Okay.
From existence. Now it does put out a little bit of radiation in that particular process. Yes, it is no longer in existence. Okay, so the energy released in carbon. No, hold on. The energy released in carbon beta decay 14 is approximately 0.16 mega eV. As alpha decay, we expect the electron to carry virtually all of this energy away as kinetic energy, because apparently it's the lightest particle produced in the decay. If we take a look at this particular guy right here, which shows a small number of electrons have the maximum amount of kinetic energy, sees the number of beta particles and how much kinetic energy they have. Excuse me, I'm gonna make sure. Yeah. Most of the electrons emitted have kinetic energy lower than the predicted value. The daughter nucleus of the electron aren't always carrying away this amount of energy. Where's the energy gone? As an additional complication, further analysis of beta decay shows that the principle of conservation of both angular momentum and linear momentum get violated. So in 1930, Pauli proposed that a third particle must be present to carry away some of the missing energy. And later, Enrico Fermi developed a complete theory of beta decay and named this the neutrino, or little neutral one, because it has an electrically neutral or little to no mass. Characteristics of the neutrino. This is super weird that they have found this, but here it is. Characteristics of the neutrino. They are a 0 electric charge, a mass much smaller than the electron, but not 0. Recent experiments suggest that neutrinos definitely have mass, but the value is currently unknown, approximately less than 1 eV over c squared. It has a spin of 1/2 and has a very, very weak interaction with matter, making it extraordinarily difficult to detect. So, actual beta decay, when you know there is beta decay, essentially what does this mean to me? First one button, there we go. In beta decay, there will always be, this is the symbol right here for a neutron. It is the Greek letter nu. It kind of looks like a curly into a V, okay? Now, with actual, it's kind of backwards. With the actual particles, with electrons and protons in existence, you actually get what's known as the antineutrino. And with your standard beta decay, you actually get the actual neutrino. So it's the antiparticles, the normal antiparticles that get the normal neutrino, and it is the normal particles that get the antineutrino in this particular case.
Excuse me.
All right. Finally, let's discuss gamma decay. In gamma decay, so for starters, you'll notice that we start up there with actually that top one is not gamma decay. What is that? That is beta decay, right? That top one right there is beta decay. But you'll notice the little asterisk by the C. Okay? Often when it undergoes radioactive decay, it's left in what's considered an excited energy state. This is extraordinarily similar to what we were talking with electrons, but it is for protons. We're not going to get into the specifics, just the fact that essentially, you know how like an excited electron can skip from n equals 1 to n equals 3, and when it falls back down, it emits a photon? This is the exact same thing, except it's not an electron doing it, it's a proton doing it. Okay? or a neutron potentially, jumping up to a higher energy state and then falling back down. And when it falls back down, where does the extra energy go? Radiation. That is gamma radiation. Now, what is more dangerous? Okay, what is going to have more energy? The proton falling down from a higher level or an electron falling down from a higher level? Well, you're 100% right, but let's discuss this. Which is going to be more energy? Essentially, a feather falling from 1 meter and hitting my hand, or the stapler falling from 1 meter and hitting my hand. So, to that end, and this kind of makes sense because probably you've already expected this already, which do you expect to have higher energy? Gamma radiation or electrons leaving gamma radiation. And to add to that, electrons falling down put their radiation over in the here's visible. They do it in the visible spectrum, right? They do it in the infrared spectrum, not that much energy. Ultraviolet we're a little bit afraid of, okay? But much more than ultraviolet radiation are we afraid of gamma radiation, right? Gamma radiation is this that we're talking about right here. So yeah, essentially you get that little asterisk right there and off we go. Smoke detectors use this all the time. They use these particular properties of charge anymore. Radon detection, carbon dating. Okay, so let's talk about carbon dating for a second here. In carbon dating, here's what, I don't want to talk about all these, but I do want to talk about this one a little bit. So, beta decay of carbon-14 is often used to date organic samples because here is the general gist. Cosmic rays, which have high energy particles from outer space, okay, in the upper atmosphere, cause nuclear reactions that create carbon-14. Okay, so rays hit the atmosphere regularly causing carbon-14. Okay, it gives it a lot of energy making these particular particles. So because of that, in the atmosphere are carbon-14 particles. So you are breathing in, or probably made up of, honestly, a ratio of carbon-14 particles right now. Okay? Now, you are replacing those carbon-14 particles with more carbon-14 particles because you are breathing. Well, that's not where most of your carbon is, but you eat. And if you eat, let's go from the beginning. So it's in the oxygen. It's evenly distributed throughout the oxygen. So your plants that are stealing all of this carbon dioxide from, I shouldn't say oxygen, I should say carbon dioxide. So, yes, yeah, carbon dioxide is where the C's coming from. So the plants are getting this carbon dioxide and an even amount of carbon-14 while they're doing it, and then they're putting that into your food. So you're getting this ratio and replacing it all the time. So if we check the atmosphere, for carbon-14 versus carbon-12, we would find a particular ratio. And if we checked you for carbon-14 and carbon-12, we should find the exact same ratio. Yes? But then you're going to die. And you're probably going to stop replacing that carbon-14. I'm going to go ahead and guess nobody's just going to do that for you. And what is this radioactive decay of carbon-14 going to then do?
Change the ratio.
Well, it's going to decay. So, if a person then were to grab a sample off of any particular living thing, it's got to be something living. It doesn't really work if it's got to have carbon in it, I should say. Okay. they grab the sample off of that. They can look at how much carbon is currently in it, and then they can backtrack how much carbon and how much carbon-12 it should be in it, right? So they should be able to predict how much carbon-14 should be in it when it was alive, and then work its way back to figure out essentially how long ago that would have occurred. Does that make sense? Now, particular arguments against this, and I will add this is only for your understanding and edification. The gentleman that had this job before me was he very, very intelligent, but he had a few interesting ideas that I don't necessarily agree with. I don't not agree with. He's interesting. Okay, so he was he's a Christian, which matters. Okay, he was a Christian that believed actually in that the Earth is thousands of years old, not millions of years old. Okay, And his line of logic, one of his line of logic, as it approaches this particular idea of carbon dating, is that what if the radiation was different in the past than it is now? If the radiation in the past was, what is it, greater, much greater than it is now, then what effect would that have on the ratio? The ratio should have then been much higher. There would have been a lot more carbon-14 around, right? So that is only to tell you, so then if there's a lot more carbon-14 in a thing, and then we go to look at it now with a lower radiation, we would assume it's a lot further in the past and not that it had a different amount of radiation. So this is something that potentially pokes holes in this. I am not saying it's correct. I will let you decide and how you want to do this, but essentially this is predicated on the fact that the radiation in the universe has stayed the same all that amount of time. To say something is 7 million years old based on carbon dating is to say you are assuming that the radiation, the background radiation, the cosmic thing has been exactly the same and has not changed in that amount. All right. So radioactive decay is essentially, here's the math for it, but we've already done it earlier. Okay, so all they essentially do here differently is they take this factor that we had earlier, this gamma times n, call it r, which we've already done. That's the rate, right? That is literally the rate. And this is the originals right here. So the rate now versus the rate original, blah, 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 do all of this. And you end up with almost the exact same idea here. Here's how much time it should have been. I'm going to expect you guys to do this math essentially from kind of the beginning up here. So I'm not going to kind of spend a lot of time on this thing explaining it because you guys can do that math. Finally, natural occurring radioactivity, you're going to be expected to be able to do this. Okay, so uranium, the 4 radioactive series. Okay, uranium is your starting isotope, and its end product is that, and half-life in years. Okay, so here's what will happen. I will tell you what type of. Basically, this is just a combination of these that you did earlier. Just being able to do that top one, being able to do the beta decay, being able to do gamma decay as well. It's kind of in succession. So I will say something like thorium goes through alpha, an alpha decay, 2 beta decays. I'm not going to expect all of these, but essentially what is that? 1, 2, 3, 4 alpha decays, okay? And then it could go one of 2 ways. So you would just go thorium to radon. How did I do that? Well, I subtracted 4 off the top. How did I get to radon? Well, thorium is at 90 minus 2 is radon is where I got the 88. So this is what we've already all been doing. So essentially, this is just, can you do these in rapid succession together? But this kind of shows what naturally is going to occur. And like I said, you're seeing half-life over here of uranium and thorium. Very, very large amount of time, how long it takes to actually get like half of that particular cycle. You will note, by the way, that all of these over here are ending in lead. Okay, I will remind you that the reason why all of them are ending in lead is all the way back. It's going to take me a minute. It's right here. There we go. Remember what we said is that the last stable element was at 82. 82 is lead. There you go. So anything above that is unstable. Anything above that, therefore, is automatically radioactive and losing part of its nuclei. How long does that take? Well, that's a half-life conversation. And it also kind of gets, as you would well imagine, just from kind of looking up there, guess what happens the further you get from 80? I mean, let's look at some of these that are the furthest up here from 80. Do you remember what I said about the color of why these were a particular color? Why is hydrogen pink? Why are the rest of these black? Why is mercury blue? Do you remember? Water, yeah, it is solid, liquid, or gas at essentially 0 degrees Celsius. So, why are all of these not have a color?
What? Or we just don't know because we haven't made enough of them?
No, they're single atoms at a time. Can you say that a single atom is water or liquid or gas?
That's what I'm
sorry, later, as I said before, yeah, solid, liquid, or gas. No, you can't until they interact. So yes, that's probably the best way to say it. All right. I think that's it. Let me check, make sure. Questions? So yeah, so you're gonna get something like this. Oh, sorry, nuclear reactions. There is one more conversation to be had real quick. Okay. So we've been talking about radioactivity. The other conversation I have down there. So we've been talking about nuclear. Hold on. No, I do need to talk about these real quick. Okay. Nuclear reactions. Here we have helium crashing into to nitrogen and producing what? Given that we also produce a hydrogen over there, notice by the way a hydrogen is 1,1 because what is in its nucleus? A hydrogen, proton, and therefore how big is it? It's just 1, so 1, 1. So we lose a proton right there, and what you're going to essentially do is some really basic math. 2 plus 6, sorry, 2 plus 6. 2 plus 7 is 9. We've already used one of them, so this is left over at 8, right? And then, of course, we have 4 plus, that's 28. We've already used one of them, so that's 27. Sorry, 27. 4 plus, oh my goodness, I was doing 14. 4 plus 14 is 18, minus 1, 17. So doing this particular guy right here. This is known as nuclear, yeah, let's just reactions. You can do that math on your own. I'm not going to make sure you do all of these. Okay, notice a neutrons, this is a neutron right here. Okay, why is it 0 on the bottom? What is the bottom left number supposed to tell us? How many protons are in it, right? So there are no protons in it, right? And why is there a 1 on top then? Does take up a place in a nucleus, right? All right, so I'm not going to have you do that because that's pretty basic. Let's talk about Q values real quick. Okay, we've actually already discussed this, but essentially it is this. Okay, what we can do to figure out an interaction is we can look at the atomic mass of these guys right here. Now, you are not. I'm going to stop you right here and say you are not going to be able to use your periodic table for this. There is a table that you want to use. It is already on the website. Come on. It's already on Google Classroom. Let's pull this up. Come on. Taking your sweet time there. Physics 2. If you go to, I think it's just chapter 29 stuff.
Say it has stuff in the title.
Do what?
Up there.
Right there. Abbreviated table of isotopes. Okay. Each isotope has a different natural U. Okay. It should be close to the number of elements, but remember that U is defined by the carbon. So you can see, like right here, for example, clicking on this, if I start to deal with, say, carbon 12 versus carbon 13 versus carbon 14, come on, taking your time. I want to get them done with the notes. Okay, carbon 10 versus carbon 11 versus carbon 12 versus carbon 13 versus carbon 14. They have the atomic mass numbers right over here. Okay, why do you have to do this, and why can't you use that guy up there? Because that's the average, and this is talking about that exact specific isotope. Okay, so you'll have to see this. Guess what stars mean? Unstable, correct. So for example, I just played the first time ever, like 30 minutes last Friday, I played No Man's Sky, and they actually have the elements out, and then you can kind of see them. It's really interesting. So there was deuterium in that particular guy right there, and deuterium is actually naturally occurring, although you can see that percent abundance right over here, say naturally occurring, but 99.9885% is your standard hydrogen as you would expect, and yeah, a hundredth of a percent is how often you're going to get deuterium out in the universe. So kind of gives you an interesting information over there. You'll also notice for unstable elements over there on the far right side, you see the half-lives. So you can potentially use those as well. But that's where you're going to get some of these numbers from. This, of course, the top we have, this is not hydrogen, this is not standard hydrogen, this is deuterium, right? How do you know that? Well, because it's hydrogen 2, standard, that's hydrogen 1. So that's where you would get this U number. Okay, so you look at the left side and you add up its total mass. And you look at the right side and you add up its total mass. And what do you notice about the two totals?
They're different.
They're different. Correct. In what way? Which one's which? Left side is greater. Now, as left side is reactants moving into products, okay, that means the total mass has decreased. If the total mass has decreased, what does that mean about energy? It has been kind of expelled. It has been used. Okay, so what we can do with this is we can find the difference in mass. We can take the difference between the two of them. Okay, and then using E equals mc squared, we can calculate exactly how much energy should now be coming out of this particular process. Okay, just take the difference, multiply. You'll remember that U is 931.5, I think, is the mega EV for a U. And in that, you can start to get whether or not, excuse me. Oh, and then this is really dumb. I don't know why they do this, but they can go like, but what if it has a kinetic energy of 5? Well, if the total amount of the difference is this, right? If the deuterion, which came in with 5 added energy in, right, then how much energy do we have in total? We would have a total of 18, just 5 plus the original number right here. That's how much Q is. Q is how much energy change there has been in this particular process. Now, let's say it wasn't 5. Let's say we just started with this. Would this be a possibly, in terms of energy, is this a naturally occurring thing, or would it take some oomph to get going? It would not. It would be natural. And the reason why is because the energy is already there provided, right? In a way, you can kind of think of this as like the ball is sitting on top of the hill. You mean, in a way, I see what you're saying. Someone's got to kick it to get it going a little bit, but then it would naturally roll down the hill. It would naturally go the way that you would expect. As opposed to the opposite, which is if the left side had less mass than the right side, in which case there is still a difference of energy, but we're going to need to add mass. So that means we need to add energy, and it's not going to be as naturally occurring. Now, one interesting thing here, and I think this is one of the only times this potentially happens, they're not being super careful with this. I have always told you that delta means final minus initial, and usually that's the case. But you will notice in order to get a positive number in this particular case, they actually did initial minus final in this particular case. And the reason why they have done that is that it's the difference of energies. You said it a second ago. Technically, this energy should decrease, right? The change in mass should be negative, right? Because it is lowering the total amount of mass. But the energy that's coming out is not, so we're losing mass, but the energy that's coming out is positive. So that's why they're doing it in this particular way. You are welcome to do it their way, or you're welcome to kind of do our standard way of final minus initial. If you do final minus initial, please understand that the sign on the energy should naturally be opposite to the sign on the change in mass. Right? If we lower mass, energy is coming out positive, and if we increase mass and that's positive, then energy is going to be negative because it's going to absorb some. All right, and this guy right over here is just going to show you that exact same thing. Okay, and it's the same sort of weird situation here with the answers on the very end. You're getting the left side, the right side from that particular guy, and you're going to notice that the second one is larger, so we have gained mass. So you weirdly get this negative number on change in mass because really what we're trying to get is a negative energy, which means it's going to require at least 1.194 mega EV in order to get kicked off. More than likely, that energy is going to come from kinetic energy. One of these particles is going to be moving fast enough at the very beginning. I'm not going to talk about that real quick. Oh, I forgot. I forgot that that next conversation was actually at the end. So there you go. That's it. It's Q energy is it. Q values. I think most of this, quite frankly, will be. Oh, I screwed that up. Yeah. No, the energy is a little bit interesting here because of conservation of momentum. Here is your equation, but I don't think you're going to require any of that. So, all right. With the remaining 20 minutes, please use this to work on the homework. Specifically, I will highlight some for you that I would suggest based on what we have seen today. I'll do that for the sake of the video.
Will you go over any questions today?
I mean, have you really started a lot of it?
There's a couple that like I've read the textbook to go along with them. There's
Okay.
some things that I'm not
Sure.
quite
We
sure.
can
Like,
talk a little bit about that.
Like,
I do need to stop like 10 minutes early to make sure I have next hour ready to go.
yeah.
I'm mostly ready,
Are
but
we
I just want to make sure.
testing?
Is that what it says?
Yes.
No. Oh, okay. Sorry. My apologies. This is this chapter. These two chapters are extraordinarily similar to the last two chapters. I tell you what. I'll move the due date to Wednesday, but your quiz is Friday over both these 29
Okay.
and 30. Yeah. So we will go over. I will go over questions tomorrow that you might have. I don't think that's going to take the full time. And actually, the stuff we cover in chapter 30, it's not the whole chapter, and it's not even like a chapter's worth of stuff. There's just a few things here and there that we want to hit. Like if you've looked ahead at the, just skipping ahead to chapter 30 real quick, pulling it up here real quick, you'll notice it's like 11 problems, and one of them is bonus, and it's pretty quick, going
So
through
I
that.
would read the textbook tonight and like start on.
Yeah, and honestly, shoot. I mean, if you get the stuff from chapter 29, the very similar stuff to what you're going to be doing here. I mean, a lot of the math in 29 is going to be those Q values that we were just talking about just a second ago, like how much energy is coming in or out of that particular process. So let me highlight a few that I would suggest you look at right now. For the sake of understanding what we were just talking about. I will tell you this real quick, if you are struggling with this. Number 2 is super finicky. In that, we'll talk about it if you're doing it. But again, the main thing I will say is make sure you're using.
What is the blue?
What was on
The blue right there tells you it needs it out to 4 sig figs, and the sig figs matter here.
Will you walk us through using the KimPad too? Before you, it's just a bunch of symbols.
I don't think so. I mean, it's just you don't need it, right?
It's on other problems. It says.
Oh, sure. Okay, I'll show you the symbol. Yeah, absolutely. Yes, that's right here. Okay, so let me actually show you the even. Let's just do this one real quick. So 6 is one of the ones I would suggest. 6 is certainly one of the ones I would suggest. Yeah, a lot of 6, 7. I mean, a good amount of this stuff that we're talking about. This energy right here, that's a Q conversation. Yeah, and then occurs spontaneously versus occurs, does it or does not, depends on Q, right? If Q naturally comes out, if the mass starts bigger than smaller, it would occur spontaneously. Small kick and it's going, as opposed to if it requires energy to go in, would be your spontaneous versus spontaneous. All right, so for starters, going over the KimPad real quick here. Let's talk about A real quick. Tell me what the answer should be for this. Bismuth 212 into helium-4. What should the answer be?
Would it be 208 over 81 thallium?
Yes. And so the way you say that, and even when you listen up there, is I'll regularly just say the element, because that takes care of the protons, and then I'll say the isotope number. So what I'll say is, because it's quicker and easier off the tongue, is thallium 208. Okay. So here's how you do it, real quick. Thallium is TL, if I'm not mistaken. Yes. Okay. So capital TL. You are welcome to use this. I don't like to. So what I do is this guy right here is just your caret. So if you just put caret, okay, you put 208, okay, and then if you put underscore 83, usually that works. Or you have to put it first.
No, it works.
I thought that would work. Let's check. It might need to be in front. No, I didn't put it right. So I think it just needs to be in front.
Underscore first.
Yeah, because it's literally going to do what I just typed in. So an electron just came out of krypton. Okay. So what should happen to the top number? Remember, when an electron, why is an electron coming out of the nucleus? What is making the element unstable?
The loss of electron.
So you're missing the previous question. No, the electrons. This is nothing of this has to do with the outside. We're always in the nucleus. Too many neutrons in the nucleus make it unstable. So if you remember that, then remember, okay, the way an electron comes out is that a neutron breaks down to a proton plus an electron. So the electron is coming out, okay, because the neutron turned into a proton plus an electron. So what's left over? You've lost a neutron, you now have a proton and electron. The electron is flown away, so the thing that's left over is a proton. So does that change the total number of things in the nucleus? No, which means we're still at 95, but what does it mean about the number of protons? Could be one more. Underscore 37. Since I don't have it sitting in front of me, somebody tell me what is what's the chemical? RB? RBs. We have the meats. All right, and then finally right here, again, you're just doing some super basic stuff here. You can see that, hey, there's 4, there's 144. So what did that have to start at? It had to start at, 144 underscore. I have 58, I have 2, so I had to start with 60. Just looking at what element is 60. 60 is...
I don't know how to say it, but it's
neodymium. Very common element in batteries.
isn't that in like
Or magnets, I should say. Neodymium magnets. ND.
We have the deets.
it just gets better.
NBs. We have the beats.
I feel like she might be being sarcastic.
Yeah.
All right. Other questions then about this?
Oh,
NBs.
22. 22. I got it right whenever I did it, but I just like alpha decay. Is that the instantaneous that is pumping?
Alpha decay is the helium particle. So you would take 4 off of this and 2 off of this. So you're 218, 84, right here. Polonium.
Okay.
Polonium.
I don't think. Period. No, I don't think they ever try to like mess you up on this. By the way, I don't think they ever like try to be like, hey, it's 84 here, but it's the wrong element. So you can use. I believe you can usually assume that if they are using this particular guy, they are using the right element here. I mean, obviously, you're welcome to check the periodic table, but. Any other questions?
Why is 23?
Why is 23?
What's happening?
All right, it's giving you basically an equation right here. It says an alpha particle collides with you just have to create it, a nitrogen nuclei. So what you do is it says an alpha particle. So you write 4,2 He. You are going to be expected to do this on the test, by the way. So please make sure that you are practicing this, even if you technically don't need to. Okay. So this plus a nitrogen molecule. And it literally said it's producing protons. So right there, right? Plus what other element? So what do I see? Well, I have a total of 28 things in the nucleus. One of them is being used. So we are, sorry, I said 28. Man, the numbers are off today. 18 nucleotides. Nucleons. Yeah, nucleons is the name of a neutron or proton, so I'm a nucleus. So 18 total, I'm using 1, 17. 9 protons, I'm using 1, 8. That's y is 23.
Well, I should have gone for Jeopardy for me.
Sure. Other questions?
Oxygen has 8 protons, it's number 8. Yeah.
The SAT for the juniors is on the 17th, right? Yeah, it's Wednesday.
We will be covering chapter 30 that day.
Just a heads up, so no predictable reason at all. Because I'm sure it's not a point. If there was a day, for whatever reason, that all of you were gone, I will not be recording a lecture on that particular day. So if you ask me to
Oh, yeah,
record a
you're
lecture,
still recording, by the way.
and everybody was gone, oh, that's a good point. So if you ask me to record a lecture,
Bye, Morgan.
Bye, Morgan.